Today we are looking at angular momentum, and we just want to quickly tackle this topic and see how we can solve questions if they come. Obviously, I'm sure they will come a question on angular momentum. So it doesn't have to be so strange when you encounter a question, in angular momentum. So I'm sure you have the concept of momentum is not very strange to you. Concept of momentum. Momentum usually talks about the product of mass and velocity. All right. So you remember just as in linear motion, we in linear motion we talked about linear momentum, and the linear momentum that we talked about in linear motion. The linear momentum that we talked about in linear motion was just when you multiply your mass times your velocity, you get your momentum. And the symbol that we were using was this one, which is called rho. Like that. It's like a P, but it's not. So this was momentum in linear motion. It was talking about mass times velocity. So we shall use this same concept in angular motion to talk about angular momentum. So in angular motion or rotational motion, in rotational motion, the symbol that is analogous to mass. What is analogous to mass is a moment of inertia, which we just denote as I. So, and what is analogous to velocity is angular velocity. Is angular velocity in rotational motion. So in linear motion we have mass, but in rotational motion we have moment of inertia. In linear motion we have velocity. In rotational motion we have angular velocity, and this is equal to momentum. And in the momentum of angular motion we denote it as an L, a slanting L like that. So that's a symbol for angular momentum. So here I'm saying that Simbarashe, you are welcome. I've seen you have joined us, Simbarashe. Awesome. I hope you are doing fine, and good to have you today. So all in all, I'm trying to, for the sake of Simbarashe was joined us, we are talking about angular momentum, and we just want to quickly deal with angular momentum and establish a few concepts so that even when you go in your test, you find a question on angular momentum, you know exactly what we're talking about. So as I was explaining to Tekla, who had joined earlier on, I was talking about comparing what we had in linear momentum. So what we had in linear momentum, if you didn't attend the class to the time when we were looking at linear momentum, we looked at it with some of your friends, and the video is on my YouTube channel. So if you want to refresh your memory on linear momentum, you can go to my YouTube channel. You'll find the video on linear momentum there. But for today, we are looking at angular momentum and just comparing linear momentum to what we are calling angular momentum. Is that, like I was telling Tekla, that in angular momentum, so angular momentum there, angular momentum is given by this symbol rho, and it is just the product of mass times velocity. All right. But when we talk about angular momentum is given by this symbol L, but it is given, instead of mass, we use the moment of inertia. Instead of velocity, we use angular velocity. So these two concepts are very similar in computation and in just in even in explanation. Really, they are very similar because the theories or the concepts that define the momentum here are the same concepts that define momentum there. So angular momentum also has to be conserved. I'm sure you know that in linear momentum, we said it has to be conserved. What does it mean to be conserved? So what it means even here for angular momentum to be conserved is we must make sure that the momentum that we have here in the initial stage where we are putting I initial should be equal to the momentum that we finally have after the collision. So this is before the collision, all right? And this is after the collision. So if we have, for example, two masses that are colliding, and then both of them are rotating, or they are experiencing some rotational motion, we can add their momentum, and we should expect that when we add their momentum by getting their moment of inertia multiplying by their velocity in the initial plus the moment of inertia times the velocity of the other one, initial, should be equal to the moment of inertia of the first one times the angular velocity final. Yeah, just like you can see here on the expression, this is what we mean by talking about when we say conservative. When we say angular momentum is conserved, is that what we have here should be equal to what we have there. So since we are familiar with the concept of momentum, let's go ahead and, or maybe you are not familiar with the concept of momentum. Let me ask, so far, do you have any questions? So far, are you following? Are you following, Simbarashe? Because take class. Yeah. You are following? Yeah. Awesome. So yeah, we have momentum that needs to be conserved. And also, let me also talk about one thing before we go any further, before we leave this concept of momentum. I'll also talk about what we call impulse. All right. Impulse. I'm sure you have heard of this word, impulse. Impulse is the change is equal to the change in momentum. All right. If momentum changes, here we are saying that momentum has to be the same. What we have here should be equal to the momentum that we have there. So if we have change in angular momentum, we call it impulse. All right. Now, how does this impulse work? So impulse is when we have torque, which are when an object is in rotational motion, all right, it's rotating like that. If there's a torque that comes to interfere with this motion, if we apply a torque, all right, the momentum or the motion of this object will change. So even if its motion will change, its velocity will change, then if its momentum will also change. So if we change its angular momentum, this is what we call impulse. Also, it's also a concept that we know in linear momentum, it's there, impulse. Even in angular momentum, it's there. So now this impulse is defined by the torque times the time of contact. So it's not just a matter of applying torque, it's also a matter of how long have we applied that torque. All right. And then when we apply a torque for a specific period of time, we will change its momentum. All right. So momentum, it will be momentum final minus momentum initial. So that is what is going to be when we talk about impulse. So we have to take into consideration, sometimes some questions will talk about find a torque. If an object is rotating and they're asking you to find a torque and whatnot, you know that you can easily use the concept of momentum. You look at how the momentum has changed, and then you look at to say, okay, if the momentum has changed, if the velocities have changed and whatnot, then I can compute my torque times time described by this equation here. And that is what we call impulse. Are we okay on that point?
Yes.
You are following?
Yes.
Okay, so let's quickly go to an example. So here on an example, we have a merry-go-round. You know a merry-go-round? Are you familiar with this term, merry-go-round? Simbarashe? You know a merry-go-round?
Yes, I.
Awesome. So we have a merry-go-round modeled as a disc. So on the flat surface, it is like a disc, and it has a mass of this much, 100 kg, and it has a radius of this much, 2 meters, and is rotating on a horizontal surface, horizontal plane, about a frictionless vertical. Yeah, so I'm sure you see the you will see the diagram. So we have a merry-go-round, it's rotating, and then this is the axis of its rotation, and then it's rotating. Usually you find that there's some hangers where people can actually even hold on to, but then it's rotating. So after a student of mass 60 kg, all right, jumps onto the merry-go-round. So here we already have a merry-go-round rotating. They haven't given us the velocity yet. They've given us just the description of it in terms of its dimensions. But then they have also told us that a student of mass 60 kg jumps on the merry-go-round. The system's angular speed decreases. So there's a decrease in speed after the collision of, so speed decreases, but mass increases because there's a student who has jumped on the merry-go-round, and the speed decreases to 2 rads per second. So now this is not impulse. Impulse is when a torque is applied, but here is just mass which is added. So when mass is added to the system, or there's a collision that has taken place, that is what we call the angular momentum has taken place, angular momentum. So the speed has decreased to 2 rads per second. They are telling us that if the student walks slowly from the edge towards the center, so the student walks towards the center, find the angular speed of the system when she reaches at the point 0.5 meters from the center. All right. So they're telling us to find the angular speed at that point. And then they're also telling us to say, find the change in the system's rotational kinetic energy when caused by her movement to the center. All right. So there's a change in the system's rotational kinetic energy, which we need to compute. And then they're also saying, find the work done on the student as she walks to the radius of 0.5 meters. So all that which we are saying is this scenario. So we have a merry-go-round which is rotating. All right, so it's rotating like that, as it has been shown here. There's a student who jumps onto this merry-go-round. And then when this student, they have told us that this student is about 60 kg. All right. So this student jumps onto this merry-go-round, and the speed of this merry-go-round decreases to 2 rads per second. So when with this student on the merry-go-round, the speed reduces. So they are telling us to say, if the students walk slowly from the edge towards the center, find the angular speed of the system when she reaches at a point 0.5 meters from the center. So what is happening is these students now start walking towards the center, and then she reaches at a point with a radius 0.5 meters. So what are they asking for? They are saying, find the angular speed of the system when she reaches at that point, 5 meters from the center. So let's see how we're going to solve it. So after the student of mass 60 kg jumps on the merry-go-round, the system angular speed decreases. That's what they told us. It decreases to 2 rads per second. If she walks slowly, that's the question now. From the edge towards the center, find the angular speed of the system when she reaches at a point 0.5 meters from the center. What strategy are we going to use? We are going to use the equation of conservation of angular momentum to find what they're asking for, to find the angular speed. We are going to use conservation of momentum. How are we going to apply it? All right. So how we are going to apply it is we use this equation. So we have the moment of inertia of the disk, which is the merry-go-round. They have told us that it is like a disk, and the angular moment and the angular velocity of the disk initial plus the student, the moment of inertia for the student and the angular speed for the student initial is equals to the student's to the disk's moment of inertia times the angular velocity of the disk final plus. So this is what we have, the conservation of momentum equation. All right. So now, since initially the student and the merry-go-round had the same angular velocity, and we know that after the student moves closer to the center of the disk, the angular velocity will change, but the student and the merry-go-round will still move at the same angular velocity. What am I saying? We know that before the student, when the student is here at this point, all right, this thing is rotating. So when the student jumps on this merry-go-round, this student will have the same angular velocity with the merry-go-round because the student is on the merry-go-round. So that is how come we are saying, we can easily say the moment of inertia of the student, the moment of inertia of the merry-go-round plus the moment of inertia of the student, if we know that this angular velocity and that angular velocity is the same, we can just make this angular velocity as a subject of the formula, because we know that when you are standing on something which is rotating, you will have the same angular velocity with it. Is it okay? Are you following?
Yes, I'm following.
Awesome. So what happens is that since you are following, then it's good. we have separated, since we know that here the angular velocity and there the angular velocity is the same for the student and for the disk. We have separated it like this, where we have made angular velocity I as a subject of the formula, and then we have factorized this expression that we have here. We have factorized it to lead to this expression that we have there. And then even here, we know that if the student, they have told us that the student moves closer to the edge or to the center here. As she moves closer to the center, the angular velocity changes. How does the angular velocity change? Because her radius has changed. She was from the center, having the same radius with the disk. She was on the edge having the same radius with the disk, but then she moves closer to the center. So, but yet she's still on the disk. Remember, she's still on the disk. So meaning the moment of inertia of the disk, even here, this expression, we can factorize it. How can we factorize it? We can factorize it in such a way that we know that this value is the same as that value because both systems are connected. All right, the student and the disk, they are connected, so they will have the same angular velocity. But of course, the angular velocity will change from the initial to the final, but that's how come we are saying in the end we'll have final. In the initial case, we had initial. Now, since the merry-go-round has been given in terms, they have said that the merry-go-round is like a disk. Like a disk. A disk, the moment of inertia for a disk is just 1/2 mr squared. But the moment of inertia for a student is not 1/2 mr squared because the student is just a point. All right, it's just they are just on one point. It's not like their mass is distributed throughout the disk. They are just on one point. So their moment of inertia will be, since this is like the center of the disk, the moment of inertia will be just the radius to the student multiplied by, their mass of the student multiplied by the radius where they are squared. So the radius is here. And initially, the student was standing on the edge of the disk. So therefore, we have the student, the radius of the disk will be equal to the same radius where the student is. Are you following? You're following?
Yes.
Awesome. So that's how come we are having this scenario where the moment of inertia for the student is just mr squared. All right. And then we know that since they are connected, they'll have the same angular velocity. But in the final stage, the disk doesn't change the moment of inertia. The moment of inertia of the disk is 1/2 mr squared, but the radius of the student changed. How did the radius of the student change? Because the student moved closer to the disk. She moved closer and came at this point. So her radius now changed. No wonder we have even indicated it by a small radius. All right. So now using this small radius, we can compute. We know this radius, they told us that she moved by, they say that when she reaches at the point 0.5 meters from the center. So if she's 0.5 meters from the center, then her radius is 0.5 as she stands on the disk, moving closer to the center. Okay. So when replacing the values, we know 1/2 here, we know the mass of the disk, we know the radius of the disk. Of course, I should have squared this one because the radius of the disk is 2 squared. So I should have squared this one. Plus, we know the mass of the student. Mass of the student was 0.2 times the radius squared. And we also know that the angular velocity of the system in the initial stage was 2. It was given that it decreases to 2 rads per second when the student jumped on the merry-go-round. The angular velocity was 2 rads per second. All right. So we have the angular velocity is what we have there, 2. So we do the same for the final. We have the moment of inertia for the merry-go-round. And as I said here, I should have put a squared because there is r squared. But a student, like we are saying, we have maintained the mass, but the radius of the student has changed. It became 0.5. We are still squaring it. So what are we looking for? We are looking for this angular velocity. And when we solve this equation, we're able to find the angular velocity as this. Is that okay? On how we have solved the angular velocity?
Yeah.
Okay. Okay, I've seen Gilbert has joined us, but I hope you'll be able to catch up where you can, Mr. Gilbert. Okay, so we are continuing, and part B is talking about find the change in the system's rotational kinetic energy caused by her moving to the center. All right. So what is the system's rotational kinetic energy caused by her moving to the center? So we have a girl standing on the edge of the merry-go-round. As she moves closer to the system, to the center, we have seen what has happened. The angular momentum has changed. In fact, the angular momentum has increased. All right. So area on, initially it was 2 meters per second. When she moves closer to the center, the angular momentum, the angular velocity increases to 2 rads per second. So what is part 2 is saying, find a change in the system's rotational kinetic energy caused by her to move to the center. All right, what is the change in the kinetic energy? We know that kinetic energy for angular motion, it is 1/2. It is 1/2 moment of inertia squared. So since we have this expression as how we can compute the change in kinetic energy. Okay, I've seen as well Precious has joined us. Good to have you, Precious.
Thank you.
Awesome. Okay, so I hope you'll be able to catch up because the class has gone even about almost 30 minutes in the class now. Hope you can catch up or hopefully watch the video because I'll be able to post it. Is that okay?
Yes.
Awesome. So yeah, so we're talking about find the change in the system's rotational kinetic energy by her moving to the center. How are we going to compute that? So let us first find out, we know that in computing kinetic energy rotational, we have 1/2 moment of inertia times angular velocity squared. So we need to find out this value of angular velocity. I mean, this value of moment of inertia. So moment of inertia I, meaning what we have initially. What we have is a system where there's a girl standing at the edge of a merry-go-round. All right. And then what happens is that this girl moves closer to the center, and we see that the system changes, the angular velocity increases, as we have found on part A. So, but as she moves closer to the center, since her radius now starts to reduce, the moment of inertia also decreases or changes. All right. So now let us see, for us to compute the change in rotational kinetic energy caused by her moving closer to the center, we are still going to use this equation for kinetic energy. But for I, for the angular momentum, we are going to divide it into I initial, and also we are going to have I final. So I initial is, we have the moment of inertia for the disk and moment of inertia for the student, for the girl, for the student. And then we know that the moment of inertia for the disk, merry-go-round has been given as a disk, is 1/2 mr squared. But the moment of inertia for the student, since she's just standing there as a mass, collective mass on one point, and then we have a merry-go-round rotating like that. So moment of inertia will be just her mass multiplied by her radius, this radius. In this case, it will be the same radius for the disk. So mass times the radius squared. All right. Now, this is what we are going to use to calculate the moment of inertia initial. And this is what you have seen when we put the numbers. The mass for the disk is this, the radius for the disk is that, and also the mass for the student is this, the radius for the student is that, gives us this value as our moment of inertia initial. So when we compute the kinetic energy initial, since we have found our moment of inertia, we'll just do 1/2, just like the formula was talking about, 1/2 moment of inertia multiplied by the angular speed. We were given that the angular speed initially, the angular speed was 2 rads per second. So we use that same angular speed which has been given to find the kinetic energy rotational initially. Then we also need to find final. Just like the way we did with finding moment of inertia initial, we also need to find the moment of inertia final, because the student moved closer to the center, the radius changed. So no wonder here on the student we are using a smaller r because the radius changed. But for the disk, for the merry-go-round, we have maintained its moment of inertia. So we have the expression for the moment of inertia for the disk, 1/2 times its mass times its radius squared. But for the student, the girl, we have just we know that the moment of inertia for the student is just mr squared, which is the mass times radius. Now her radius changed. Here it was equal to the same radius for the disk, but here the radius changed because she moved closer to a distance of about 0.5 meters from the center. So her radius changed. That's how come even her moment of inertia changes. When we compute the moment of inertia using this expression, we find this value, 215 kg per meter squared. All right. So now, how do we compute also? Because we want to find a change in rotational kinetic energy. So change in rotational kinetic energy, we know that at the end of the day, change in rotational kinetic energy will be kinetic energy final minus kinetic energy initial. Now, we are saying that kinetic energy final as well, we are going to compute it by getting the moment of inertia final, 1/2 moment of inertia final multiplied by the angular velocity final, just like the way we did initially there. So we have found our moment of inertia. We know that the velocity, as we have just calculated, we calculated it here, angular velocity as 4.09 rads per second. We use it even here to find the kinetic energy final. And then after computing it, 1/2 times 215, which we have found, times 4.09 squared, we have found that the moment of inertia is, the kinetic energy. Kinetic energy is now 1800 joules, 1800 joules. So to find what they are talking about, the change in the system's rotational kinetic energy, is what now we use kinetic energy final plus minus kinetic energy initial, and subtracting the two, what we had found here minus what we had found there is 1800 minus 880. We get this as the change in kinetic energy. All right. So kinetic energy was not conserved because there's a change. If kinetic energy was conserved, we would have found a 0 here, because it would have been kinetic energy final minus kinetic energy initial. So even that question which was asking to say what is always true about the angular momentum, or what is always true about a collision, right? So they are talking about momentum. So momentum is always conserved, but you will find that kinetic energy is not always conserved. As we can see, if kinetic energy was conserved, when we do kinetic energy final minus kinetic energy initial, we're supposed to find a 0. But since kinetic energy final and kinetic energy initial are different, then kinetic energy is not always conserved. It's only conserved in elastic collision, So this is what we have on this point. But there's also another question which we are going to do. But so far, do you have any questions so far? Do you have any questions so far? Simbarasha, Precious, Gilbert, any question?
The radius for herself, was it mentioned in the question, or?
Yes, it was mentioned.
Finding inertia, moment of inertia.
Yes, the moment of the radius for the student changed when she moved closer to the center. The radius, the radius changed, and the radius was mentioned in the question. Here, when she reached at a point 0.5 meters from the center. So if you have the center like that, and you are at a point 0.5 from the center, that is your radius. If you have moved, if you were here and then you move to a point 0.5 closer to this is the center, your radius will change from that one on the top to the point where you have moved to. It was mentioned in the question. It's just that you joined in a bit late. We had already seen the question, but of course, like I said, I will. In fact, I had sent this document, so you have it. You can even counter check, and then you can as well rewatch the video, which I hope to post on YouTube. But yeah, any more question before we move to the other question? because there's another question, one last question that we need to look at. Okay, so there's this other question that we need to look at. It was a test question, but before that, there's part C to the question that we're looking at. Part C is saying, find the work done on the student as she walks to a radius of 0.5. So find the what? The work. All right. So work is actually, work done on the student is just the change in kinetic energy for the student. So here we are looking at the whole system. We're looking at the change in rotational kinetic energy caused by the movement. So we're looking at the moment of inertia for the system, for the disk, and for the student. We're combining everything. But at this point, we just need to talk about the student alone. In fact, Zoom is saying it's about to go out, but you can still go back to the link. In fact, let me just end this meeting right now so that when we come back, we can just continue properly. Yeah, that is if you want to come back. Yes, so I'm going to end this meeting so you come back right now. Yeah.